Welcome everyone to the 22nd session of Podium TED Talk series brought to you by Asiata Digital Labs. We're delighted to have you all with us as we embark on a journey into understanding CAP Theorem and IT's implications for microservices. Our podium today is graced by a speaker who brings a wealth of knowledge and expertise to the discussion. Let me introduce you to our speaker today, Thamodi Wickramasinghe, a senior software engineer with an MBA from the University of West London, who has obtained a AWS architecting badge and is an active member of AWS user group Colombo with a total of 5 years of experience in the tech industry. As we navigate through this enlightening session, we invite you to absorb the valuable insights our speakers has to offer. Without further ado, let us hand over the reins to our speaker. Over to you, Thamodi.
I hope everyone can see my screen. So good evening, everyone. I'm Thamodi Wickramasinghe. Today, I'm planning to talk about what CAP theorem and its implications for microservices. So I'll be covering introduction, as in I'll be talking about what is CAP theorem and how we can apply CAP theorem in microservices. And while applying a CAP theorem into microservices, what are the practical considerations that we need to consider, and also the real world use cases, how CAP theorem has been used in different microservices, and the best practices and recommendations for using CAP theorem in microservices. So let's look at this example. Everyone must be confused that I'm here to talk about CAP theorem. Why do I have a Netflix logo? So I would like to ask you one question. Has anyone ever faced any inconsistencies while watching Netflix? Shuara, can you create a poll? So has anyone ever faced any inconsistencies in Netflix? Let me see the answers. Okay, 71% says no and 28% say yes. I watch Netflix a lot and I have faced inconsistencies in Netflix. So let's look at this example. So for an example, let's say if I'm watching an episode from Big Bang Theory, and then after I close it, the viewing history does not instantly refresh. It takes some time to update the viewing history. So there are some inconsistency issues in Netflix. So with that issue in mind, let's talk about CAP theorem. So what is CAP theorem? CAP theorem, it is also known as Brewer's theorem. It was introduced by a computer scientist called Eric Brewer in 2000. There are three aspects, which are consistency, availability, and partition tolerance. So basically, in CAP theorem, it states that in a distributed system, it is impossible to achieve the three aspects that are consistency, availability, and partition tolerance simultaneously. That means at the same times, we cannot have these three aspects altogether. So that is what CAP theorem basically means. So now that you know about CAP theorem, let's look at these keywords as well. That means consistency, availability, and partition tolerance. Okay, let's talk about consistency. Consistency means all the, like in a distributed system, every node in the cluster returns the same and the most recent and successful write. I know in the audience we have some non-technical people as well. So consistency means all the nodes will have the same copies of a replicated data item which is visible for various transactions. That means every client will have the same view of the data. Let's elaborate more on this by looking at this diagram. So we have data center 1 and we have data center 2. In data center 1, we have node A and node B, and data center 2, we have node C. So from node A, when the user X is writing, the node A will replicate to node B and node C. Until that replication is completed, readers are blocked. That is what consistency means. So actually, this is an example of strong consistency. So this is one of the key areas of CAP theorem, which is consistency. The next aspect we have is availability. In a basic nutshell, availability means it should be available. That means each read or write request for a data item will get a response. That it can either be a successful response or a message saying that the operation cannot be completed. No matter what, if a microservice has availability, it should get a response. So that is what availability means in CAP theorem. So every working node returns a valid response for all the read and write requests in a reasonable amount of time. So next, we'll move on to partition tolerance. Let's look at this example. We have nodes, 4 nodes, N1, N2, N3, and N4. And these nodes are accessed by service 1, service 2, and service 3. So even though we can see that the connection between node 2 and node 3, it has been broken. So even though node 2 is disconnected, still service 2 must be able to get a response. So in general, a partition is a communication break within a distributed system. It can be a lost or a temporary delayed connection between two nodes. So in a distributed system, we must guarantee that partition tolerance can gracefully recover from partitions once the partition heals. So now we know about what partition is. Partition tolerance means that in a given system continues to operate even with data loss or system failure. A single node failure should not cause the entire system to collapse. So based on the previous example, even though this connection break is there, service 2 must be able to get a response. That is what partition tolerance means. Then we have these 3 categories. That means CP versus CA versus AP. That means we can create categories. Like basically the CAP theorem means at a given point of time, we can only have 2 aspects. We can either have consistency or partition tolerance, consistency or availability or partition tolerance. So in the CP category, every read operation receives the most recent write or an error. That means we have consistency and partition tolerance. And CP systems can withstand network partitions, ensuring that the system remains operational even if communications between nodes is temporarily disrupted. But in the CP category, we do not provide availability. So for the CP category, we can use MongoDB, HBase, Memcache, Bigtable, and Redis. Next, we have the CA category. CA category means we have consistency and availability, but we don't have partition tolerance. So CA systems maintain strong consistency and ensures that all read operations returns the most recent write. Since it provides availability as well, every request receives a response, even it means sacrificing consistency or tolerating network partitions. But CA category does not provide partition tolerance, so may experience downtime. So based on this diagram, CA category means all the RDBMS. That means Oracle, SQL Server, MySQL, likewise. Now we have covered CP category and the CA category. Let's look at AP category. AP category means we have availability and partition tolerance. So in these systems, every request receives a response And the AP systems are designed to withstand network partitions, allowing nodes to operate independently and serve requests despite communication failures. But there can be data consistencies. Based on the diagram, the AP category, clients may read inconsistent data. So examples can be Cassandra, React, and CouchDB. We have covered what is CAP theorem and the types of systems. As I mentioned earlier as well, explained earlier as well, in CAP theorem there can only be two aspects at a given point of time. So we have discussed all the systems CA, AP, and CP. So now let's talk about how we can apply CAP theorem in microservices. When applying CAP theorem to microservices, the trade-offs are evident. A trade-off means that if we are achieving one outcome, it means we have to give up something else. So for specific requirements, we have to cater to the, based on the specific requirement, we have to choose the trade-offs. Let's say if we have certain critical data, we can use consistency. And if we have user responsiveness or something related to that, we can use availability. And for robustness, we can use partition tolerance. So it is crucial when applying CAP theorem to microservices. What are the trade-offs? So these are some of the practical considerations. We have the consistency versus availability and the partition tolerance. Microservices tackle different business logic with complex data. So if one microservice requires strong consistency, we have to sacrifice availability. Let's take a simple example. In a financial system, we have to handle day-to-day transactions. So the balance needs to be updated regularly. So we have to choose consistency over availability because it is crucial to have consistency in a financial system. So we should ensure that all nodes see the same set of data, even if it means some nodes may not be available for requests. That is for a financial perspective. Let's take a social media platform. So for social media platforms, they don't require consistencies. Like sometimes we can be shown something else. So they don't value consistency compared to partition tolerance. In social media platforms, we require partition tolerance over consistency. So it is okay for different users to see slightly different versions of the same thing for a short period of time. So as a result, the system will remain available even in the face of network partitions or failures. So based on the requirements of the projects, we need to decide which aspects we are going to give priority to. So we can either choose consistency and availability or partition tolerance, or based on the systems I've explained, we can select what are the trade-offs going to be. And I have a question. Shwara, can you post the question? Can anyone tell me what is eventual consistency, or has anyone ever heard of eventual consistency? So eventual consistency means over time, the system converges towards one consistent state. However, during the transient period, users accessing different data centers may observe different versions of the data. I know this contains technical terms, so let me try to explain it using a diagram. So we have data center 1 and data center 2. And in data center 1, we have node A and node B. In data center 2, we have node C. So much similar to the earlier diagram I've explained, we have a write operation, and in eventual consistency, till the data is being replicated, it does not block the operation. It would show the old one. So that means that as a result, there can be inconsistencies, but even though it would eventually be consistent, like over a period of time. So implementing eventual consistencies in microservices is very critical. So we have to have proper data synchronization mechanisms and conflict resolution strategies, and also we can use event sourcing and distributed databases, which would support eventual consistency when applying eventual consistency in microservices. So we have to anyway prioritize two aspects. Let's say if we does not prioritize consistency, we can use eventual consistency, just like in the diagram. So there can be few inconsistencies for a shorter period of time, but it would prioritize the other two aspects. So the next one I would like to talk about is partition tolerance in microservices. So microservices must be designed to handle network partitions. As I explained earlier, network partition means a communications break between two nodes. So we can improve, partition tolerance can be improved by using a technique called sharding. And also we can within circuit within microservices, we can implement circuit breakers and retry mechanisms if there's any network failures. Let's take a simple example. In a cloud-based environment, network partitions can be a common occurrence. So when a network partition occurs, microservices need to decide whether to prioritize consistency or availability. As I explained earlier, we can use sharding techniques. And so microservices must sustain, and it should not break because due to a single database or service failure. As a result of single database or service failure, it should not lead to a whole system outage. So while applying CAP theorem in microservices, we need to consider partition tolerance, and we can implement circuit breakers and retry mechanisms as well. So the next one would be polyglot persistence. Polyglot persistence means like when designing microservices architecture, we can use different databases for different microservices. And as a result, we can allow microservices use the most appropriate data storage technology based on their need. Let's consider a simple example. Let's say if we have a e-commerce platform, okay, and it has multiple microservices. For managing inventory, financial, and payment-related data, we can use relational databases. To store user details and product catalog data, we can use a document database. And let's say if we need to store social network data or social media data, we can use graph-based databases. So for different needs, we can use different databases. So we can use polyglot persistence as well. And we can use different databases for different microservices. So these are some of the real world use cases. As I explained in the first slide, Netflix has some inconsistencies. I faced a lot while I watch an episode of Big Bang Theory, or then I quickly close it and come to my viewing history. It does not update the data. Let's say if I'm watching the 11th season 10th episode, and if I come to my viewing history, it can still show as 10th season 9th episode, something like that. So there are some inconsistency issues in Netflix. because Netflix prioritizes availability over consistency. So that means it should be available all the time. Even if it fails at some point, it should show the results rather than in consistent data. Another example I would like to mention is the Netflix's recommendation system. Along with the viewing history, the recommendation systems can be also considered as one example. So it should be available to all the users at the same time, but there can be slight consistencies. The next example would be Uber. Uber's microservices architectures prioritizes partition tolerance. Even if there's any communications break between nodes, it should ensure that the platform is operational and responsive even in the face of network disruptions. So Uber would prioritize partition tolerance over consistency and availability. So this emphasis on partition tolerance contributes to a robust and reliable system. So these are the two examples I have used. I'm sure there are many more. So the next I would like to talk about is the best practices and recommendations while implementing CAP Theorem in microservices. So when designing microservices, we should keep CAP in mind. So when designing microservices, we need to make sure based on the requirements of the project, which aspects we need to consider, what are the trade-offs, which aspects we'll be using, and in order to let's say for an example, if we choose if we don't use consistency, we use availability and partition tolerance, we need to make sure how we can manage consistency in that microservices architecture. And the next one would be monitoring. We need to implement monitoring tools to track the performance of every microservices. Based on the performance, like while monitoring, we can identify some other requirements. Let's say for a given period of time, like when we first put the system into production deployment, the requirements can be something else. And then after like 2 to 3 months, the requirements can vary. So based on that, we need to have monitoring tools. And based on that, we have to check the trade-offs, how it can be changed. This is quite similar to the second point as well. The evolution of microservices architecture over time. So microservices architecture can be changed over time. As the system evolves, the trade-offs can be different. Like I said, the initial production development and after 6 months or after 1 year, the trade-offs can be changed. So therefore, we need to regularly revisit the design choices, and we need to make sure we are using the correct aspects from the CAP theorem. And then based on that, we can do some modifications and changes based on technology and overall ecosystem. So yeah, the key takeaways would be I've explained about CAP theorem. So CAP theorem consists of consistency, availability, and partition tolerance. So I've explained what are those three aspects, and we have different types, three categories, which is consistency and availability, consistency and partition tolerance, and availability and partition tolerance. So based on the requirement of your project, we can decide which aspects we should prioritize, and based on that, we can design the microservices architecture. Even though I emphasize on CAP theorem, there are many factors we need to consider while implementing microservices. So I have this QR code. I have written an article on 10 challenges of implementing microservices. You can scan it and you can check the 10 challenges. So not only CAP theorem, there are multiple factors we need to consider while implementing a microservices architecture. So this is the QR if anyone wants to scan it. So everything I've talked about today, what is CAP theorem and the types of systems and how we can include in the microservices architecture. I have written another article on understanding CAP theorem and its implications for microservices. If you want to access and if you want to provide more feedback to my article, you can scan this QR code and then you can access that article and you can read more on the CAP theorem and microservices architecture. So that is the end of my presentation.
So before we wrap up, a big thank you to our speaker today for sharing her expertise with us today. And we appreciate your time and knowledge. And thanks to everyone who joined this session today. And we will be having more sessions in the coming future. So thank you and looking forward to seeing you all at future podium sessions. Have a nice evening.